I sincerely thank the organizer for making me a part of this. Normally, we don't get a chance to have a discussion and talk about this kind of technological aspects of it. I'm mostly an academic person who does a little bit of research. So for me, it is a kind of very intriguing to get to hear about so many technological advances that India has made over the years. As far as today's discussion is concerned, or today's my presentation is concerned, I will be, because of time constraint, I'll be only focusing some of the aspects that we do in the lab, particularly focusing on sustainability. But before I go to that particular part, let's focus on the major player here. So this is normally my group, mostly just for the students. These are all MSc students who have worked in our lab, and we are really fortunate to have them. They are now well placed either in industry or they'll be pursuing their PhDs also. But in addition to that, there are four major areas that we normally work. One is related to energy and environment, materials, mostly on the nano side, then catalysis and organics. So as far as organics part is concerned, today we will not discuss too much about this part, but mostly we'll try to restrict ourselves towards discussing about this. So along with this, now there is one part that keeps coming every time when we start discussing about science. So the part that we keep discussing is particularly sustainability. Now I know that the term sounds cliche because we have been hearing this since I was a child. So, but unfortunately, during my study, no one has told me, we heard the term, but no one has told me the ways to make a particular process or technology sustainable. And now we are old, or I'm not that, hopefully I'm not that old, but now the problem for us is actually, it is very challenging to get an idea and make it into a sustainable thing. So that's why I encourage all the youngsters who are here, so start thinking the sustainability term when you start developing your own ideas. Okay? Because eventually, at some time, we cannot keep on thinking somebody else will do it for us. Okay? It's not going to happen. It's better we all come and start taking a lead on this. So now, along with this part, another aspects of this so-called sustainability is waste to wealth. And most of my presentation I'm going to be talking about at least that point. Utilizing certain waste material and how we can try, at least our attempts, to convert into something which is, so to say, a better version of the waste. Okay, but definitely it has some good purpose to be utilized for. What next? So before I joined Vignan, actually I have been privileged to have been working or have been involved with certain projects which lead to generate lot of good publications. But interestingly, knowingly or unknowingly, you see, if you look at all these, you see the particular metals or the figure that I showed, all of them except this one, all of them, knowingly or unknowingly, actually comes under this regime. So that means that when we are doing, we knew about it, but we are not aware enough to make sure that we can continue with it. But anyway, this is one part of this. So most of the things are based on catalysis, which I will not discuss this today because that is what we have been doing. We will continue to do it. But when I joined Vignan, then the next thing comes, what is next? What we can do, because obviously being in a private university, we have certain limitations in terms of availability of instruments and all these things. So what is next? What we can do? So we have to, some way or the other, start thinking in the context of what is available and how to make it work. So as simple as that. So we start asking questions, what's next? And in this case, we started asking questions, mainly 3 questions. If you can answer for your part, most likely, most of the things are going to be solved or taken care of. Solve is a very big word. We cannot solve the problem just like that. Okay, Sir, I was mentioning 45 years. And think about that, I am 45 years old. So since my birth, everything is put into just to make only one product out. So solving is, for youngsters I'm only talking, solving is a big term. So do you have a problem to tackle other than the catalysis which you are focusing on? So one thing that we found out that there is one problem that we can tackle, that is the treatment of dye-contaminated water. Why? Because even after discussing for more than 30 years, we are still not guaranteed a single material which is going to do the job for all. In fact, because this was not my field when I started working on it, the more I started working on it, I thought that should be the question that I should be asking, that should I make only one product which can solve this purpose? More I started working it, I realized that it is not going to be like that. You need to make your choices which material to be used for what kind of dyes. Okay? So as far as this is concerned, this is a very schematic diagram of why you need this, is that you generate in industrial scale, you generate a lot of dyes, especially in textile industry, and they come into the downstream, and eventually what happens is that somewhere or the other you need to take care of this, and this is where our nanotechnology can help us tremendously. We have these options that are available to us. These are the materials that are also available to us. So you just have to mix and match, but except that you cannot take anything just out of this box and start mixing with this, because you need to know what these dyes are and how they will interact with your materials and in which mechanism. So apart from that, there are few challenges which exist in the areas of this so-called treatment of dye-contaminated water. The challenges are the efficiency, which I spoke about. Not a single material can solve all the problems. Regeneration and reusability. From academic standpoint, we started seeing lot of articles which says that this dye can do this, this material can perform outstandingly. But we now, except in last 5 years or so, before that, we hardly saw anywhere where they started mentioning these parts. That becomes a problem. Yes, we can publish 100 papers out of this, but irrespective, we can never get out a product out of this. Because if you can't make it sustainable, one of the sustainable conditions to make it reusable, that's not going to solve. So there are mechanistic insights. In fact, then we later found out that one of the reasons why we keep having these problems, that we have very minimal idea about how this mechanism works. Yes, from chemical engineering aspect, we have a lot of things to talk about. But unfortunately, we still don't know exactly how this is done. Okay, so we need to tackle this. There are synthetic challenges associated with the nanomaterial that we do. We cannot really synthesize a nanomaterial which can be very, very expensive and does very efficiently. Even if it can do very efficiently, that is not going to be a sustainable choice. Last but not the least, there's a validation study. Sir was mentioning about using computational power to validate your whatever technology or process or material that you have made or any kind of process. The earlier papers also like that.
So the challenge is the cost effective.
Cost effective, we'll come to that. Don't worry. We'll really discuss. So when I say efficiency, that actually takes care of this cost effective ones also. Efficacy also, I should have mentioned efficacy, correct? So now, the second question that I had asked is that, do you have enough background to tackle such environment point? When at the beginning, we, along with the students, we decided to have a meeting. We said, do you have enough background? The answer is no. That time it was actually an answer which was no, because we didn't know how to do it. So what is the solution? Solution is, if you don't know something, just don't shut the door. Just go and explore. That's what we did, actually. So we started discussing and exploring further things. So as a snapshot, what we are going to do is we are now picked up a very few so-called combination of dye and adsorbent, and we'll make sure that we learn from them. They are not from waste materials, but they will give us enough information to take it forward so that we can develop something which is more cost effective. Okay. So the first two that we tried is, one is the halosite, one is the pyrophyllite. Interestingly, there are a lot of literatures on this, because they are clay materials. So huge amount of literature that are already there. Unfortunately, there are not that many literature on their absorption efficacy. In last 10 years only, this actually started exploding. There is a very specific reason for it. The reason was that people knew about their structure and everything, but only thing they did not know how to correlate with those structures with the adsorption part. So, and they are natural nanoclay. Again, we are not doing anything, so to say, extensively expensive in order to take it forward. So, in few slides, I'm going to just summarize some part about those things. So, this is how halosite looks like. It's a clay material, it's a layered material, which is an aluminosilicate. And eventually, this is your dye. This is a cationic dye that we started. Somehow it's not very good. Anyway, we'll see. So these are all technical aspects. If you are really interested, I'll be happy today. Because of time paucity, I don't want to spend some time. The adsorption part, experiment, especially for youngsters, very simple. You take a dye solution, dump halosite to it, or your material to it, and you see whether it's absorbing or not. You can calculate how much it's absorbing based on a lot of the other data as well. And you can come up with a theory or the mechanism related to it. But again, does this solve the problem that we actually discussed? So these are again some of this little bit characterization. These halosites are nanotubes, just to show. 5 minutes, sir. So now in this case, we have also done some other things, IR, BET. Unfortunately, this is not a very, they are not porous, so that's a challenge we can relatively, definitely improve on. So we are still working on it. These are certain batch adsorption study to show how the percentage of removal actually varies with respect to time, amount, dye concentration, and temperature.
This one in 5 minutes.
Oh, 5 minutes, the first one. Yeah, okay. This is the validation study that I was talking about. Okay. So in fact, we did validation. We showed that how instead of having this particular one, where you use one factor at a time process, we can actually make sure that how the interdependency of different factors lead to the optimum efficiency. So we can recycle it. That was something that was missing in the big previous literature. So, and we did some, so to say, kinetic and thermodynamic calculation to find out whether the process is exothermic, endothermic, whether it's spontaneous or not. Based on that, we came up with a mechanism to show that this process is governed by a lot of diffusion parameter. In addition to that, depending on the which pH range you are working, we actually have different types of mechanism. The second one is a pyrophyllite nanoclay. It's pretty much, it's very simple to that. It's again a clay material, but one interesting part that we found out in this case and as well as the halosite case, that on the contrary of a lot of other researchers who have said that there will be a so-called interlayer adsorption, we found out that explicitly it is dependent on the concentration of the dye that you are using. Because at a low concentration, what we found that most of the dye is going to be on the surface only. We have proven it by IR and all this thing, XRD. Once you keep on increasing the dye concentration, there's a possibility that it can go in. But there's also another possibility that there will be a multi-layer adsorption on the surface. Okay. So that makes it, this adsorption mechanism, very, very challenging. Because depending on your pH, depending on reaction condition, depending on your concentration, everything is, all the mechanism will change. So what I wanted to say is that just having one particular data point at a certain concentration will not solve the general problem as such. Okay. We still have a long way to go. This is, for time being, is the same thing. How it works, what are the characterization. But eventually here also, we came up with another mechanism depending on both the surface charge on the pyrophyllite structure as well as the pK of the dye. And we said that it's predominantly dominated by so-called Coulombic interaction. We did recyclability as well as our regular RSL, response surface methodology, to find out the interdependency of different parameters. This is pretty much the mechanism. Now, when I say decontaminated, I sent this to a paper. They said, okay, you say decontaminated, but it's actually not decontaminated. And I appreciate the reviewer actually, because when I say decontaminated, it means it should be free from everything, right? This is not free. You have this additional bromide ion here. We are not removing the bromide, which we need to. These are the certain things which are completely ignored in the previous literature. We appreciate that. We have said, yes, we'll change that one. But I wanted to show that these are certain things that you need to make sure that you have some way or the other defend or tackle those problems. So what's next? So we have already solved this problem. Second one is, the third question that I said, the third question is, can you extend this for this acquired knowledge that you had for the idea to incorporate the notion of waste to wealth? Again, maybe, because we don't know. But then that time, we are very excited because now we know what to do with this. I know how to do with this. So what we have done there, we take this idea, and we move it to something, another different types of adsorbent for its same similar dye, but that is called nanocellulose, which is actually can be obtained from different waste materials. In this particular case, this is a waste-derived material. The waste that we have taken is nothing but coconut coir. We have taken this is a standardized procedure. It is not very, we should also appreciate the amount of work that is done. This is a standardized procedure to remove all the lignin and other side products for this to finally get the nanocellulose. But when I did this, does it actually look like nanocellulose? That question came into picture. We know that we can solve this problem. In fact, it looks like this. See? So they are, in fact, tubular structure of nanocellulose. We can characterize them. We can do a lot of other kind of study. We did again batch adsorption study, and we found out that after regular thing, we can also do this recyclability part. So this is, think about this, slowly from your natural K plant, we are moving to a nanocellulose part. Now nanocellulose, which is waste derived, it is not only can absorb this, but at the same time you can actually make sure to recycle this multiple times. So that means our job is done, is it? That's the second, last question. So last question is this one. With this I will stop. What's next? Because up to this is a story that I said, okay, we started with this is how we developed, and we followed. What is next? Can we start using one kind of waste to get one type of material, but with multiple applications? This is our next goal. How did we do that? Again, we have taken these parts, but we extended that to something else where we change eggshell. Now, you may find that there is no relation with halloysite, cellulose, and eggshell-derived materials. But there are, in terms of sustainability concept, there are certain relations. We have tried to move from so-called this natural nanoclay towards this waste-derived system. Now, you know eggshell, how abundant it is. It is not, and most of it, there are also literature on this. When we started doing this, we got excited, so we said, okay, we only focus on this part. But later we found out people have done eggshell based, especially because you know all the eggshells are calcium enriched. So they have used this as a supplement, calcium supplement. They have used this as a catalyst for a lot of reaction, especially for bioethanol production. Right? So we said we cannot then just outcompete those parts. So, but we can still start working on this. We can use this to utilize this as a nano vehicle for the drug intercoupling. So slowly, from this concept of the knowledge that we have from dye, we are now using the similar thing to develop a drug delivery system. Another one, we can also utilize that and use as a non-innocent support for CN coupling reaction. So how we did it? This is a very simple procedure. Not that anyone with a furnace which can go up to 1,000 can do it, because it does not need any fancy other things, no gas or anything. It's a muffled furnace thing. So you take eggshell, you just reflux it to get rid of all the organic impurity, then you hit it at 800, you are going to get this calcine eggshell powder. If you use that with copper 1 or copper 2, you are going to get this one. Why copper 1 or copper 2 will be clear in a second.
What is the atomic number of Ethereum?
Which one?
ET.
This is ethyl. Ethyl alpha. No. This is not a metal. It's just so now this is what we did. Now what we actually did, we took the calcium Excel. 2 minutes, I'll finish it. Calcium Excel powder, very nice we have done. It's very simple to do. We used an intercapone. It's a very important drug. Why? Because this is a drug that is used for it's used for Alzheimer and other stuff. It has very low bioavailability. It does not stay. Even if you take 100 grams, it does not stay in your body. It goes up only, I think, less than 30% bioavailability. Okay? So, in this case, what we have done, we have said, okay, can we combine this with calcium eggshell, which is calcium enriched? So, we are going to provide a particular drug with both the things where you have a calcium supplement as well as the original drug. So, this is, at this stage, we have made calcium supplement, it is a dual drug delivery, higher absorption, sustained release, biocompatible support. So in fact, we did that. This part is not published yet, but we have done this adsorption part, we know that it works. Only part is the remaining part. Again, all these so-called simplified version of adsorption processes are already characterized and already proven. Only thing was, we still need to know. These are
the first cycle efficiency is not comparable to the earlier, 95, 97%.
This one?
Yeah.
No, because the problem here is what happens. This is a pH range. This is not
near 90.
No, this is pH, sir. Actually,
that's pH.
That's because we cannot. That's the problem that actually sir pointed out. That's the problem. The problem is, it is not the adsorption that we are looking into. It has to dissolve also in your body, right? Otherwise, there is no point having this. So,
whichever the pH, this data pertains to first cycle, right?
Only first cycle. Correct. That is correct. Only one cycle only we did because our job is to take it to the next level. But desorption, we are still working on it. It's a little bit challenging than this. What happens was, depending on the pH, or whether it's you are taking industrial pH or any other pH, your calcium starts dissolving. So the adsorption amount that you are thinking you are having is not actually going to be there. So you need to think about that. In addition to that, there is a problem in intercapone structure. We struggle for more than 6 months on that. When you change pH, intercapone changes its structure. Okay, because it got 2 OH units. It's a catechol based structure. Catechol based structure.
Goswami, just conclude please.
Yeah.
Just last slide.
Last slide, yes. That's the last slide only. So we have done that for the catalysis part also. We know that this is the one which is working. Again, not up to the mark. Normally, people are used to getting 90 above percentage. We are not going there, but I still think that it has a potential to be taken to the next level. With that, I think I have done those. This looks promising, not finally there yet. So we have done this. With that, I would again like to thank Sir as well as organizer, as well as all the participants.